Welcome Chemistry 1007 students at ULM. This is Dr. Pryor with basic concepts of chemical bonding. Moving forward, we did cover some of this in class, but I just want to make sure we got a full view of it. And remember, for the test, I will tell you the new material that will be on here. All of this may or may not be on here. Some of you are very familiar with much of this material coming in here from your high school background, but we'll go a little more in depth. There's different types of bonding, which you've already acknowledged. Ionic bonding is between metals and nonmetals, where electrons are not shared. They're completely taken or lost by an atom. And we saw that with sodium chloride or potassium fluoride. They lose electrons or they gain electrons to become anions and cations, and it is the electrostatic charge that gives the attraction. Some are very soluble in water. Covalent compounds, on the other hand, are like sugars, and they are bonds between different nonmetals usually. It's not always nonmetals, but it's primarily nonmetals that are on the right-hand side of the periodic table. And then we have metallic bonding, which we haven't talked about very much because it has to do with more industrial and electronic applications. And that is a sharing of electron orbitals. And we learned a little bit about orbitals. We'll learn more in chapter 9. Lewis symbols. We can draw the covalent dots to represent the valent electrons that are available in metals or nonmetals. And for lithium, for example, it only has one dot, and beryllium has two dots, and boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon has a stable octet. Sodium has 1, magnesium 2, aluminum 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, and argon, again, another stable noble gas. Developed by G.N. Lewis, it helps to understand the reactivity with respect to the possible bonding electrons or the donated electrons or where the accepted electrons will go. All we do is use a dot to represent the electron. We often note that with these lower n number like 1, 2, and 3, we're often able to satisfy the energetics by the octet rule. We'll learn later on that there's something called the 18 electron rule for d and f orbital containing metals and such. Here we can do a really cool experiment with chlorine gas, which looks a little bit green as the cartoon shows us. We can drop pure sodium metal that has its electron, and the reaction will transfer an electron from sodium completely over to the chlorine, and chlorine can even then gain the electron and become a chloride anion and a sodium cation, which has lost its electron. Lots of energy comes off, the temperature raises, and we form this solid sodium chloride from these basically solid in a gas reaction. We see sodium solid and chlorine gas reacting and doing as such, releasing very exothermic, lots of energy coming out from the bonds breaking and the reforming of electrostatic charges. Ionic bonding can also be diagrammed here with an arrow, and we show an electron being transferred to the chlorine, and the sodium loses an electron, so it therefore becomes positive. Chlorine therefore becomes negative. We saw this before, but let's add something else that we've learned. For example, an element can readily give up an electron, which is sodium, and sodium has low ionization energy, which is endothermic, but low in this case when it's in a gas state. And then we also have the high electron affinity of chloride. So we're combining the two concepts of ionization energy and electron affinity. And chlorine has a very high affinity to gain electron. In fact, it's exothermic and helps for the release of energy in this reaction that you saw on the last slide. And so this is what happens. We're familiar with table salt. And we can look at the structure, and we know that sodium is not real strong. It's got a high melting point. It's crystalline, as you've seen from looking at table salt. It's kind of shiny and bright when light is reflected upon it. and it is kind of well formed. And some crystals are not well formed. There's even better ones than sodium chloride where they're very distinct and very shapely. Where as opposed to being very shapely and organized, it can be very amorphous where they hardly have no recognizable shape. Looking at it under a very powerful microscope and using X-ray diffraction and all sorts of stuff that's beyond the scope of this class and my expertise, sodium crystal structures form what they call in the solid. This is, of course, not in water. This is when it's solid and all the water is driven away. They form these crystal structures called body centered cubed, where there's 8 atoms at the corner of a cube and 1 atom at the center. And that you would learn more about in inorganic chemistry. So there's all these really unique lattice structures that these ionic compounds can form. The energetics, I don't want to get too involved in this because it's very stepwise dependent. And although enthalpy is a state function, it's independent of the pathway, but we can look at the process, and therefore we can look at path dependent processes um, to kind of see what's happening when we take a sodium chloride solid and we convert it all into its gas ion phase. And what occurs here? So we have sodium chloride solid, and let me turn on the very useful laser pointer. We have right here, we have this sodium chloride here at the bottom of this plot that's here on your right. Sodium chloride's a solid. Of course, this is something to think about in perpetuity. Anything that you see on the planet, any rock formation, any solid formation of any type, any geological formation, you have to realize there were other alternatives that could have formed when this formed, whenever it formed. And whatever you see is the most stable structure at this time where you can't be real high energy because it would be unstable. So these elements could have came from something else, which they did. We came from the stars. Of course, we know that this is likely true, however we were made. We came from the stars, and things were very hot temperatures, and things coalesced and came together and become energetically stable. That's why they exist for us to even see them. So you can imagine the formation of sodium chloride had to have been somewhat exothermic to even form and to even exist on the planet, which we can find in ocean beds and things like that. So, but we can also see where sodium chloride would have been a gas at very high temperatures in outer space, and chlorine would have been a gas at very high temperatures in outer space or during a supernova or some explosion of a creation of the universe, whatever happens, the Big Bang. But and that's with any compound. So anytime you look at something, you know that that is the energetically stable version at this time, and something must have been much more higher energy, and it came down to be stable, able to be a real product that we could look at, a real material, a real alloy in the earth. Sodium chloride's no different, but simpler, because alloys sometimes can have 7 or 8 different elements, and it can get really fun and also complicated. But if we were to look at the Born-Haber process, we could do this many ways, but if we want to go path dependent, and enthalpy is path independent because all we care about is the summation of the enthalpies and the standard formations of enthalpies. We can look these all up in tables. I'm not sure. We don't really need to do that at this point. Our tests are quick and fast, and we just need to kind of understand concepts and some numbers too. But we have sodium chloride that's a solid, and it can be heated up to where the sodium's still a solid, but the chloride actually becomes a diatomic gas. And then we can heat it up even more, and the sodium can now become a gas along with the chloride. Then we can heat it up even more, and we can break that diatomic chlorine structure to get monoatomic chlorine. And we can go further, and we can take the sodium and we can ionize the sodium, which takes more energy. All of this was endothermic from this solid sodium chloride to this sodium cation that's in the gaseous state that's giving up an electron. And then we could have chlorine gas existing as a monoatomic chloride neutral species that takes on the electron because it has an attraction for an electron. It has an exothermic electron affinity, and now chlorine has the negative charge on it in sodium gas. and hasn't changed the energy at all in the terms of enthalpy. Because remember, enthalpy is a lot like heat, and enthalpy is also a lot like kinetic energy. So it's kind of like three things in one. And then the energy of these gaseous anions can come down to form a solid. And this sodium cationic gas and this chlorine anionic gas coming down to form sodium chloride solid, that is all lattice energy. Lattice energy, anything that's a solid versus its gas has to be exothermic. It had to give up energy to go from gas to solid. It had to give up a lot of energy, right? So we know that lattice energy, if we see the lattice energy as a positive number, we know that's the amount of energy we have to put into a solid to make it into a gas and its cations. But if we see the lattice energy as a negative, we know that this is how exothermic it was from its gaseous species in the anion and cation formation, and then becoming a solid. This is really cool stuff. Many things affect ionic bonding. And so this is a complicated process that doesn't need to be too overcomplicated. Just understand the steps a bit. There's more to look at here. We talk about the energy to create a cation is endothermic. We have to put in energy, but the energy to form an anion was exothermic, as you saw on the previous slide. The formation of a solid releases huge amounts of energy. It's exothermic, which is part of the lattice being formed, the lattice crystal formation. So this is really cool. You could heat up a crystal and turn it into its gas phase, and you could figure out how much energy that takes. You have to heat it up, so you have to provide fuel, either electricity or burn petrol fuel or solar power. So this applies to any ionic compound. The Haber process it sort of applies to any ionic compound that you can think of. It's going to have different energy levels that we'd look up in a table. And now we can think about the energy level being part of the enthalpy of formation, the standard enthalpy of formation. Anytime you see this naught, that means the standard enthalpy of formation, which often means kilojoules per mole, whether that be often it's going to be negative, of course. But we're not interested right now in doing these calculations. We are interested in this lattice energy of 788 kilojoules per mole, and it's positive. So we know that to take that solid and look at the reaction, that helps answer the question. Taking the solid and turning it into a gas, cations and anions takes energy, which makes sense. Turning something from a solid to a gas must take energy. Now, if we were to reverse this process and rewrite this equation in the reverse, sodium cation plus chloride anion equals sodium chloride solid, we would have a negative 788 kilojoules per mole, and we would want to reverse this value. And so the definition is to separate 1 mole of solid ionic compound into a gaseous form is here 788 kilojoules per mole. It's going to be positive if we're going this direction. So we have to think about the direction. Now we have this nice, beautiful table, and you can see lattice energy is different for different ionic compounds. And interesting, as these anions and cations get larger, the lattice energy goes down. And as the anions and cations get smaller, the lattice energy goes up. That means smaller cations and smaller anions bind more tighter? Yeah, sort of. And there's more energy involved in holding them together, so it takes more energy to break them apart. And then we have other things to think about, such as the charges on the cations and anions. That can affect things. Greater charge, greater attraction. And we'll see the equation here in a second. But all these compounds, lithium fluoride and cesium chloride, these are soluble in water. Sodium fluoride, lithium iodine, they're all soluble in water. And magnesium chloride and strontium chloride, you have to remember you need two chlorides to provide 2 negative charges for the 2+ on magnesium, the alkaline earth metal. And the lattice energy goes up here. The charges went up and the lattice energy went up, which makes sense when we see this equation, which I do want you to memorize, or I'll put it on the equation sheet. And we have strontium chloride, which is similar, but then we go to magnesium oxide. the lattice energy goes up, calcium oxide, and then strontium oxide, and then the energy goes way up for SCN. And this is very high. Now, strontium chloride and magnesium chloride still remain soluble in water, but not magnesium oxide, not calcium oxide, not strontium oxide. Lattice energy can tell you how strongly two atoms or more might bind to each other. So it could be very important, right? So here is the magical equation. The energy here, the lattice energy, we could look at it, energy of the lattice. We have this constant kappa, which we may or may not need to include. We may not need an exact number, just a relative number, but we can get exact numbers. But we have Q1 and Q2. That's the charge on the cation and the charge on the anion, right? If we're just dealing with two atoms in an ionic bond. Then we have the diameter, which could be the radius or the absolute diameter. And think about the equation. Now, if the diameter goes up, or the size of the atom goes up, or if the space between the atom goes up, any of those things that make the distance between the two charged species, the cation and the anion, go up, anything that makes the distance larger, such as a larger atomic radius, perhaps, will make this energy smaller, right? So less lattice energy, greater and greater distances mean less and less lattice energy, okay? But we got to think about relative terms. Now, in the numerator is the charge. The greater the charge is, the higher the energy is going to be between the attraction between the atoms or the ions that are attracted to each other. And so we can see here where lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and cesium chloride, the lattice energy goes down. It goes down here. And it goes down because the distance is increasing here, decreasing E. D is going up, driving the energy down. And cesium is larger than lithium, and rubidium is larger than lithium. So it's decreasing the energy in the lattice bonding energy. And also the size, we know that lithium has a much smaller radius and therefore will enhance the energy compared to cesium. Cesium has a much bigger radius than lithium, right? They're referring to the lattice energy here, right? Increasing charge, of course, increases the energy, right? Decreasing size increases the energy, increasing charge increases the energy. Decreasing charge will decrease the energy, increasing size will decrease the energy. So we have to really understand what's happening here. So electron configurations of the ion, we have a lot of times we just only have to worry about the octet rule. But when we get into transition metals such as d electrons, we start getting into 18 electron rules, which is ionic compounds. Transition metals don't follow the octet rule. They often follow the 18 electron rule, but they don't even do that all the time because of energetics, because something may not need all the electrons to be energetically stable, and that's inorganic chemistry. And we are finished. There's a lot of cool stuff here. I'll be back with some more for Chapter 8. Thank you, Chemistry 1007 students, and study and do well. Talk to you later. Dr. Pryor.